gave up on that.
Yeah, well, it's recording anyways. Okay, so today we're going to work a lot more on Lewis structures and try to finish the chapter, so we're going to kind of move a little fast. So one of the things you have to remember is formal charge, right? So I'm going to teach you a couple of things about formal charge real quick. So let's say you have a structure and it looks kind of like this. Just do, this is methyl alcohol. And then I ask you to tell me what the formal charges are. What's the formal charge? Well, it's the charge that the atom appears to have based on the number of electrons that are around it. Yeah, there we go. Let's catch it for a second. And I can already tell you, like when I draw this, and pretty soon when you draw this, you'll look at that and go, the formal charge is 0. There's no formal charges. And the way you tell that is, remember we talked about Lewis dots, right? So like carbon is this, and then oxygen is this, and hydrogen is this. So when you look at those atoms, like these Lewis dots of these atoms, you say, well, carbon needs 4 bonds. So any combination of 4 bonds is okay. Oxygen needs 2 bonds and 2 lone pairs, and hydrogen just needs 1 bond. So you can look at that and say, well, this carbon, let me do it in green, this carbon has how many bonds? 4, so it's 4, and no lone pair, so its formal charge is 0. So you can just tell by looking at its Lewis dot what it's supposed to be. And because, you know, in organic chemistry, we're only dealing with about 6 elements most of the time, you're just going to have those. Yeah, chin-ops. Chin-ops will be in your head. You'll know how many valence electrons and all that kind of stuff. So this formal charge would be 0. The oxygen is supposed to have 2 bonds, right? And 2 lone pairs. And the reason I can say that is because it has 2 unpaired electrons and 2 lone pairs of electrons. So that's what it's supposed to have. And if you look at this oxygen here, 2 bonds, 2 lone pairs, formal charge is 0. So you actually don't have to do any calculations for those. Those, if it looks, here's the rule, if it looks like it's Lewis dot, the formal charge is equal to 0. It's important you get good at this, because what's going to happen is when we go to some of the different drawing styles, we don't show the lone pairs, but we have the correct formal charge. And so you have to know how many electrons are around the atom based on its formal charge. Okay?
So no lone pairs and all bonds filled is a formal charge of 0.
For carbon.
For just carbon.
For oxygen, it's based on its Lewis dot, it's 2 lone pairs and 2 bonds. Because these, right, it doesn't have its octet when it's like this. It needs to share another electron in each one. So we've got 2 here, 2 here, 2 lone pairs, and 2 bonds. There's 2 lone pairs and 2 bonds, then the formal charge is 0. For nitrogen, what would it be? All right, think about where's nitrogen in 5 valence electrons. So nitrogen looks like this. Hang on. So that's what the 5 looks like, right? So how many bonds will it have? 3, and what else will it have?
2 lone pairs.
A lone pair, 1 lone pair, yeah, 2 electrons in a lone pair. But yeah, it's like it's the same lone pair. Yeah, so nitrogen, like in ammonia, for example, it will look like this. All right, formal charge is 0.
Yeah,
Right, because it's got 1, 2, 3 bonds in a lone pair. So that's a very quick way to tell if the formal charge is going to be 0. Now, here's the other thing, though. You have to still be able to figure out what the formal charge is. And so I wrote the rules there. I'm going to have you guys learn this. So I made this up. call this thing the valence state. The valence state, the term has been used for other things in the past, like in the early 1900s. By the way, I gotta take this off. I don't know who wears a badge. The valence state is what you have to do is you have to count each electron and count bonds once. So for example, for carbon in here, the valence state is 1, 2, 3, 4. What is in here? 1, 2, 3, and then you got to count each electron. Count each electron, so it'd be 1, 2, 3, 4, 5. That's how many electrons it has. It has the 5. And so, how many is it supposed to have? It's supposed to have 5. So you take the valence electrons, the 5 valence electrons, you subtract the valence state, which is 5, your formal charge is 0. So you can calculate just based on that concept what the formal charge is. So we're going to apply that to a whole bunch of different atoms. Okay, so let's do that. And if you have questions, feel free to stop me. And again, as a reminder, if there's something that's confusing but you don't feel like stopping me, write that time down. That time right there is the time of the lecture, and you can always go back. Even like when you're asking me a question online, you can say, Dr. K, you were working on this thing and I didn't understand it. It's in 6 minutes of the question.
Which of these atoms form valence state should we memorize?
Well, the valence electrons, carbon, nitrogen, oxygen, fluorine. You remember
Chin-ups.
Chin-ups? Remember the chin-ups thing I said the other day? Carbon, hydrogen, nitrogen, oxygen, phosphorus.
Chin-ups.
Sulfur.
Sorry, say that again. Carbon, hydrogen. I got carbon, hydrogen. What else?
Oh, sorry. That's this.
Yeah.
It's the thing I said in my CHNOPS. Because it sounds like chin-ups. That's why my professor, remember that? I told that story. Yeah. Those are the ones you should probably remember the number of valence electrons for. But I mean, reasonably speaking, you'll have a periodic table if you just want to check. You just look at the periodic table. It's the group number. But like anything like this that you do all the time, it's useful to just know what they are. I wouldn't make a conscious effort to memorize these things. I would just keep doing it over and over again. It's 5, 6 things.
It's going to become muscle.
It'll stick in your brain eventually. Okay, so we're going to fill in some formal charges. We already did this first one. That one's 0. That's a formal charge. So what we're going to do now is we're going to use this little formula to do it. The valence electrons for carbon is always 4, right? So what I'll be writing is like the math for this. This is 4 minus 4. That's 0. That's just following that equation. So the formal charge is 0. What about the next one? 4 minus 3. That's a plus 1. So this is a plus like that. This is actually known as a carbocation. It's a carbon cation. It's a special kind of beast. We see a lot of it, though. In organic chemistry, it happens all the time. You don't think about it. It's usually in an intermediate of a reaction that's formed. Sometimes in resonance structures it's formed. But yeah, we see it all the time. What's the formal charge of the next one? 4 minus 5. Because there's a pair of electrons here. So you would count as 1, 2, 3, 4, 5. And this is minus 1. What the plus and the minus essentially say is when it says it's plus, it means essentially this carbon's lost an electron, so it has a positive charge. And this one says, oh, it's essentially gained an electron, so it's a negative charge.
When there's two of them, you count them as one, right? So it's 1, 2.
No, when it's pairs,
Yeah.
you just count each one.
Oh.
Yeah, so this is 5. Like 1, 2, 3, 4, 5, like that. I like being able to write on this. So nice. And like if I stand here on the board, my hand gets in the way. I'm sure you guys don't really care that much. And then this is called a carbanion. It is also really common. What's this last one? It's got one electron. So, but it's 4 minus what? 4. It's also 0. But it's part of the accounting of the charge, right? Is counting all the electrons. See, these two electrons aren't shared. That's why you count both.
It's just one electron. It has a bond. It's sharing one electron.
Is there a partial charge?
Each bond is
Not really. This one is neutral. Oh, so I forgot to put the minus here because I got all carried away. This one is 0. This is a carbon radical. A radical is any odd numbered electron species. So this has got an odd number. You can really tell it's a radical because it's just got a dot instead of a pair. Yeah, bless you. Okay, let's do nitrogen. So you do nitrogen, I'll do nitrogen, we'll all do nitrogen, but I'm not going to say anything. You look up and you'll see what you got. But how many valence electrons does nitrogen have? 5. Okay, so that's where we got to start. By the way, when I'm done with the chapter, I'll save this file and I'll post it. So all the writing will be up there. So if you miss something, you can get it. Sometimes I'll write and you'll see this, because when I print these, you'll be like, where was that in the lecture? It was at 12 minutes. Let's go to 12 minutes. I know it seems stupid, but it just makes it life easier.
I keep wanting to put 6 minus 5. I don't know.
Yeah, it's always start with the valence electrons, right? That's what you always have to start with valence.
The valence state is the number of electrons plus the number of bonds.
Yeah, number of unbonded electrons plus the number of bonds, yeah. It's a little bit different than the way they teach in Gen Chem. This is actually how I started teaching in Gen Chem now.
Yeah, I remember you introducing this way during the review for the exam lesson.
Yeah.
Nice.
Yeah, it's just cleaner. Yeah, it's cleaner. It's the same math. It gets the same number, but I just...
Yeah, just by combining them plus the electrons and bonds together in this valence state makes them look like...
Okay, so I'm gonna draw some bonding patterns. I couldn't think of a better way to do this, but let's start with all single bonds. Carbon's gonna look like this, right? What other ways could carbon have 2 bonds? Or 4 bonds, I'm sorry. Double bond, right? So I could be like this. I could have triple bond. But then what do I have to have? Single bond. What else am I missing? You could do a double and 2 singles. Those are all patterns that you'll see. And the reason I do this is I want you to get used to the idea that when you see this, it doesn't mean, or you see the 4 dots like this, That's actually what I meant to do. When you see the 4 dots like this, it doesn't just mean 4 single bonds. There's a whole variety of kinds of bonding patterns carbon can have. Carbon turns out to be able to have the most kind of bonding patterns. It's one of the reasons why it's central in all of organic chemistry and all of biological chemistry. It can make the most types of structures. Okay. So nitrogen would look like this. So what can nitrogen have? It can have a triple bond, right? Oh, sorry, I drew carbon again. What else does it have to have if I do that? Lone pair, has to have the lone pair. And then I could also do, sorry, I don't know why. I could have a double bond, a single bond, and a lone pair, right? You could also have 3 single bonds, which is really where I wanted to start, but I just let you guys do it. Any other combinations? Like this isn't, I'm going to draw this over here. This isn't unique, right? It's just a rearrangement of that middle one. So that's why I don't draw it. What's that? Conformer. Yeah, conformers. Yeah, that word. Oh, she was asking, is there a name for when it's rotated differently? It's called a conformer.
Oh, conformer. How do you spell that?
Don't worry about this word yet.
Look at that. I'm good.
Yeah. Yeah, oh, it's a conformer. Yeah.
Transformer.
Yeah,
But we call it conformer.
but I didn't know how to spell it.
It has to do with the emphasis. Get it? The emphasis. Yeah, never mind.
Okay.
All right, oxygen. Oxygen's Lewis dot. Like that, right? So what do you expect? You expect 2 bonds, right? 2 lone pairs. So you're gonna, this with single bonds, it looks like that. You can have a double bond, it can look like that, but then it'll have to have 2 lone pairs. So these are the patterns that you'd expect to see whenever it has 0 formal charge. Now fluorine is simple. It has to look like that because fluorine only has it has 7 valence electrons, so its Lewis dot looks like that. And hydrogen is simple. It looks like that. That's Stephanie. You're Stephanie?
Yeah.
Oh, who's Stephanie? No? Sua's here. Aaron. And then I have a Stephanie Quellar. Who are you? Oh, do you want to add the class? Okay. That was hard. I'll give you ad slip later. And you're taking the lab too?
I already took it.
Okay. Yeah. So yeah, that's no problem. I'll give you an ad slip. It's like I could fit so because I came from City, we have bigger classes. I have had 60 students in an OChem lecture. Yeah, to me, this is like, and you guys are all the students I like, so yeah, that's better. When you get 60 in a room, you're just like, well, I don't know about that one. I probably shouldn't say that so openly. Okay, yeah. Now, okay, you still have to know how to do this because sometimes it's hard to draw Lewis structures just by looking at the dots. And so you will learn how to do this. I'm not going to spend a lot of time on it. I'm just going to go over it real quickly. To draw the Lewis structure for nitrate, this is like the way you learn in Chem 1A, right? You draw a skeleton. This is the skeleton. And you count valence electrons, or total number of electrons, and you distribute them onto the skeleton. So once you've distributed the electrons onto the skeleton, you can actually sit here and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 pairs of electrons. That's the 24 valence or electrons plus the charge that were distributed onto the structure. And then the last thing you have to do is satisfy the octet rule. And to satisfy the octet rule, you're going to look at this guy and say, oh, look, incomplete octet, 2, 4, 6. So what do you have to do? You have to draw a double bond, and that's how this structure comes up. That's the final Lewis structure. And then the last thing you do is you fill in formal charges, right? I know that's really fast, but this is review stuff. So let's see now. How do I do the formal charge? Well, the way I just taught you, you would say for oxygen, right? Its valence state is, valence electrons is 6. Its valence state is 7. That one's -1. Now this oxygen, right, when you look at it, what is the formal charge for this oxygen? 0, because it's got 2 lone pairs and 2 bonds. So the other oxygen is just like the first one. Oh, I could have said one of these oxygens, not like the other song. Dang it. And then the nitrogen. The nitrogen, it's 5 minus 4, because there's no electrons free on it, so it's +1. So this is 1. Like that. Now there are resonance structures to nitrate. Resonance structures exist anytime you can make the double bond, for example, from another atom. It doesn't have to be an oxygen. It could be something else with a lone pair on it. So one of the resonance structures would look like this. I won't draw everything, but it'll look like this. And the other resonance structure will look like this. And you can fill in all the dots. Okay. But simply speaking, I took this pair of electrons to make that double bond, and I took this pair of electrons to make that double bond. So it can come from 3 different locations. There's 3 resonance structures, and every time you have a resonance structure, the structure is more stable. So anyways, I've got more to talk about resonance structures in the next chapter, so I'll just hold off on talking about too much. Questions?
So we're determining the charge of a whole compound. You take the formal charge of each element or each atom in the compound.
Yeah, you can add it together, and it'll be the charge of the ion in this
So
case.
that whole ion should be
-1. Yeah. So because it's nitrate. Oh yeah. So because it's nitrate, right? So ultimately, when we finish these, we put brackets around them and a minus charge. And that's how you would draw it. And I guess if I wanted to make it look pretty, I could get rid of some stuff like this, but that's
cool. You can just remove strokes like that.
Yeah, and I should be able to put them back on easily too, but I don't know how anymore. There's like a button to push and it disappeared. I can configure this toolbar any way I want, and apparently I configured it off the toolbar. I know. Technology. All right, moving on. So now what we're going to do, we go backwards. We're going to figure out the number of electrons based on the formal charge, and then we're going to talk about different drawing styles. There's a lot of different drawing styles. So again, formal charge is valence electrons minus the valence state, right? So I'm going to look at this carbon, right, and say to myself, it's got a -1 charge. And this is a real common drawing style where we don't show lone pairs of electrons. It's called a Kekulé structure, but anyway, we'll get to it. Names. So for this one, I would say for A, this is I saved some space over here. So let's call this A. For A, I have a formal charge of -1, right? And then carbon has how many valence electrons? 4. And so my valence state is what I'm solving for. And what do I get? A little tricky because of all the minus signs. 5, yeah. Valence state is 5. So I have, on this carbanion, I would have, I'm going to count them out. 1, 2, 3. So how many electrons do I need? 2. And there's 4 and 5. So that's the lone pairs that would be on that structure. A lot of times, like I said, a lot of times in organic chemistry, in fact, most of the time, we don't draw the electrons. We just keep track of formal charge. And so you're supposed to know what the electrons are. Okay, let's do sulfur. This will be for B. Its formal charge is +1 now. How many valence electrons in sulfur? 6, yeah. I know. No periodic table. The only thing missing from this room, minus the valence state. So what is it? 5 again? Yeah. And then it's going to be, again, 1, 2, 3, 4, 5. 1, 2, 3. This is 4 and 5. And then for the oxygen at the end, this is for C. It's going to be -1. Valence electrons is 6, yeah. So the valence state is 7? Yeah. Yeah, it's not 5 again. That would have been nice if it always came out to 5. And then we go 1, and then 2, 3, 4, 5, 6, 7. And when you're done, most of the time, not all the time, but when you're done, most of the time you're satisfying an octet. D is the only one in this page that doesn't, actually. So what's the formal charge there? It's +1 again, right? And then I have, sorry. I just, weird random thought. 4, it's carbon, like, -3, oh, sorry, minus the valence state. The valence state is 3. I'm like 4 minus 3. No, never mind. That's what I'm solving for. And so when you do 3, you go what? 1, 2, 3, and you're done. And so it doesn't satisfy the octet. It only has 6 outer electrons, and that's the carbocation that you saw before. I don't know if you noticed. Like I already drew this one earlier, and it was the same. And I drew this one earlier. It's the same. And what's going to happen is eventually you won't even do that. You'll be carbocation. Just leave the electrons off. Carbanion, leave the electrons on. It's just going to be second nature to you. But until you get there, that's how you do it. Moving on. Yeah, so what's a Kekulé structure, right? A Kekulé structure is a Lewis structure without the dots. You've got to put the formal charges, because if you don't put the formal charges, people can't figure out how many electrons there are. So these are all examples of Kekulé structures. Like the Lewis structure, the only difference, the Kekulé is equals Lewis without dots. Now the dots are important when we do right chemical reactions. If the electrons are involved in resonance, or if they're involved in the reaction as it's taking place, we will draw the electrons in. But for how many of you like drawing all those dots? Nobody likes drawing all those dots. Turns out chemists don't like drawing the dots. You like drawing the dots?
I make it look cool.
Okay, well they look cool, and having to draw them 100 times every lecture is 2 different things entirely. I agree, they look cool. If you need to put the dots in, you can fill the dots in. How do I know how many dots to put in? Because I look at oxygen, it doesn't have a formal charge on it, so it has 2 lone pairs and 2 electrons, 2 bonds.
So calculate structures will have formal charges on them. Like
Calculate structures have to show the formal charge. It just turns out in all of these, there's, yeah, because they're not showing the dots. You either show the dots and calculate formal charge and put it on there, or you don't show the dots, but you have to put formal charge then.
yeah, because I mean, it's like otherwise you have no way of knowing the formal charge. You
Yeah.
have some way of showing
Yeah,
it.
if you don't have a way of knowing how many actual electrons are there, yeah, exactly. That's why we do it. So you can actually fill these in. That would be the Lewis structure, of that calculate structure.
So no formal charge.
Calculate, by the way, is the
Yeah,
guy
it's-
who was attributed with the first, like, realistic idea of what benzene looked like. Benzene's this cyclic molecule. People argued a long time about what the structure of benzene is, and it turns out benzene looks like this. But there was a lot of data, experimental evidence, and he said it must look something like that, and he was right. He was the first guy to get it right. That's why he's kind of famous. The other reason he's famous is it said that he had this dream about a snake chasing its tail, and that's how he came up with the structure. Yeah. And then it's also famous because it said that he was on like morphine or heroin at the time. He was on drugs. He came up with this idea. Okay, so that's a calculate structure. We don't have to get too sidetracked on the funny organic chemistry stories. But then there's also condensed structures, and I'm not going to spend a lot of time talking about like condensed structures. We'll practice it, but what do you see here? It's the atom, right, followed by the things attached to it, and then the subscripts to show the numbers, right? CH3O, CH3, that would be this one. Now the reason the O is here is because it's actually in between the two, right? And then this one's a little harder. This one gets written a whole bunch of different ways. This hydrogen is written to the left, and then C double bond OO, that's CO2H, or more commonly, chemists will write it like this, HCOOH. That's the HCO, yes, HCO. Yes, right. That's more commonly how you see it. And then for amine, the nitrogen has these 2 on it, right? The carbon has 3 hydrogens on it, and then it's attached to the nitrogen. So basically going left to right, everything on that atom is generally written to the right of it. Your book has much more formalized ways of saying all that, but you can see how that happens. Okay, but we're in a practice, right? I can say you can see it, but, there's always. Of course, and then I didn't pick the simplest ones. Okay. So we're going to make a condensed structure out of that, out of A.
To the right and then Jim.
So what I'm going to do is I will look at this, and this is the first thing that I'll write. And I'll write it as CH3. And then it's CHBr. Now I'm going to leave the bonds in between, and then I'll condense it down further. I just want you to see how I'm consolidating everything. And it'll be CHCl. And then it'll be CH2. So this is for A, in case you weren't sure. And then it'll be CH3. So you can see how I consolidated all that, right? I left the bonds in between. CH3, and CHBr, and then CHCl, and then CH2. You see how I did that? Everybody see that? And then what you do is you just get rid of the bonds. You just squeeze it all together. Right. So then you write it like this. And then it's really confusing. But you just get used to it. After a while, you look at it and you learn how to parse things out because you know carbon can only make 4 bonds. And so you're saying to yourself, well, there's 3 here, so it must be connected to this carbon. And then there's 1 here, 1 here, 1 here, 1, so that was, you just get used to seeing that. Now, sometimes in calculated structures, okay, when we're drawing them like this, oh, and I'll show you other structures, drawing types that I like, that are even simpler. It's a lot less writing, okay? Sometimes you'll see it like this. And the reason you might do this is because the bromine might be doing something in a reaction. So you only call out the part of the molecule that's going to be doing something. Okay? So like this is like partially condensed. It's partially a calculated structure, partially a condensed structure. There's lots of these sort of hybrid drawings that get done. Okay. What about B? Yeah, let's do B. So I'm going to have CH3, O, and then CH2, right? So that's CH3O, CH2, and then you'll notice this has a nitrogen on it, right? And 2 of the units are the same. So just like you would write H2, you don't have to, you can do CH3 in parentheses and drop a subscript 2 on it like that. Or you can draw it out and partially condense, depending on what's going on. Oh. Something happened, I don't know what. Oh, curse you. See, the recording stopped. Disconnected. All right, so the last one, let's go ahead and do that. You guys could have done it without me. So I'm going to do this. I'm going to condense all of that. And I prefer to, but you don't have to, I prefer to do it like this. Because I want to have a CH3 to the left of this carbon. So that whole unit is to the left. So it's CH33C and then CH2. So that's this. You see how that is? But how many CH2s do I have in a row? 2. So normally when there's 2, you would still write it out like this, but I'm going to show you another option. And you know, like on a test, I'll give you a formula like this and say, draw the calculate structure, or draw a line structure, or draw it. And then you have to read this structure, interpret it, and draw it. And then I'll ask you to name it and do all kinds of other stuff. But then you could also do it like this. And the only reason I know somebody would do something like that is because they were putting it on a test and they were trying to make it stupid crazy. But yeah, that's very cool.
So like for an example, if you were to say like draw a condensed structure, since there's so many different ones, is there like a specific one that you look for?
I am really good at recognizing OK structures. Yeah, and they're all written. All OK tests are all written. So I just look at it and go, yeah, looks reasonable. But then if it's like got too many bonds on something, or you drew it in the wrong sequence or something, then I'll see that too.
Okay, why can't you go? Why can't you connect the 2 C? Is it?
Why can't you connect
There's a
the 2 C?
CH2.
Which C's?
That.
These?
Yeah.
What do you mean they are connected?
No, I mean like why can't you put C2? No, it's different.
C2? Oh, yeah, it's different because this C is bonded to B. Well, yes, because this C is bonded to these 2. That's why. I know that does look weird when you see naked carbons. I know it's kind of embarrassing and everything, but Yeah, I got a call the other day. I was actually driving home from another appointment with my mom, of course, and I got a call from that former student who was in my OChem class 2 years ago. Yeah, 2 years ago she finished, and she was calling me to ask if I could be like a letter of recommendation because she wanted to be a teacher. And I said, oh yeah, that's really cool. She had gone to UCLA. Her mom didn't want her to go, but eventually went to UCLA. And then also she got in pharmacy school. So she was calling just to tell me got pharmacy school. It's really cool. And so she was going to try to teach and be in pharmacy school. And she just got mad. I don't have to do all that. But she was saying, by the way, this is the whole reason for bringing it up. I was asking her like about whenever I get these calls from like former students I haven't talked to in about a year. I asked them like, so what was valuable like coming through the class? And she said the written tests. Written tests, the multiple choice does you no good, she says. But the written test is what prepares you for university work. And so I will stick with written tests as much as I hate grading them. It takes me days to grade a written test. I know, sorry guys. The class this size should only take me half a week.
So you're giving us written tests in this class?
Yeah, all written.
They're not estimates.
And you can see why already, like the structure drawing stuff, multiple choice, it's probably more confusing as a multiple choice than it is to actually draw it yourself. Because when you draw it, you might draw it in a different shape, that's okay, but then you look on a multiple choice, there are so many different ways. Just to draw this, with the OH going up and the chain going down, and these two onto the left, these two onto the right, this one here, this one there, you could just, right? And any one of those would be right, but on a multiple choice, none of them might show up except for the one you didn't think of. So there is a skill in multiple choice, but she said the ability to have fewer questions and read deeply into the question and work hard on a question were the most valuable things about the tests and stuff. So, all right. And I've heard that before. That's not the first time.
I still have multiple choice because I have a chance.
Yeah, multiple choice, I have a chance, right? Yeah. Okay, so then there's also skeletal or bond line structures. And in a skeletal structure, you're not, it's like a Kekulé structure. You don't show lone paired electrons. And you don't show hydrogens attached to carbons unless they're, for some reason, you're trying to call them out in the structure. So you'll notice there's, on this one, see, don't show C's or H's that are bonded to carbon, right? But like bromine you would show, and then OH you would show the H on it, and NH2 you would show the H, but it's just carbons that this rule applies to. So I'm going to go 1, 2, 3, 4. There's 4 carbons in that, right? So when you draw these, and you see I have to draw a 4-carbon bond line structure, or 4-carbon skeletal structure, you're going to go like this. There's 1, 2, 3, 4. Every zig and every zag, right, and the ends are carbons. That's a carbon, that's a carbon, that's a carbon, that's it. And if you need to say, well, how many hydrogens are here? Without looking at the formula, right? There's 2 because it has 2 bonds, so there got to be 2 hydrogens there. Huh?
The sticks, I call them sticks.
Stick drawings? Yeah, people call that. Bond line, like, so if you're going to look up for extra help online and stuff, typically they're called bond line drawings or skeletal. But if you do skeletal, sometimes you get the drawing of the loose structures, and then it's not as clear. It's a lot of different stuff.
Just get pictures of skeletons when I look stuff like that up.
Yeah, right. Oh, yeah, or other things, and you're like, how did that come out?
I know, it's like,
So here, there's 2 carbons here and 1 carbon here. So like a methyl group looks like that. That's a CH3. It's just the end. It's a stick. Right? And you can see already like how much faster this drawing style is. This is the one I like to use in class the most. This is the one students like to see the most. Right?
No.
Yeah. They like seeing, I'm going to be serious with you, typically students like seeing that. I don't know why. But when you get to cyclic structures, look at how much cleaner they are. These are cyclic compounds.
I think those have words.
I like the cyclic ones.
Hmm?
I think they have letters. Yeah.
You have the letters, and it's easier to look at. You know exactly how many hydrogens. It's just more information. But seriously, this is what everybody does.
Well, like not all, like that pentagon-shaped structure could have other different hydrogen bonds, so it doesn't give you that much information.
Well, no, it could only have 2 hydrogens at each carbon. All right, because there's already 2 bonds.
And it needs to, because it can't
Yeah.
just have 1 hydrogen. Because those ones over there have double bonds.
Yeah, these have double bonds. So if you were to draw that, like if you wanted to draw the hydrogens on here, which is often done actually, drawing hydrogens for different various purposes, you can draw it like that very quickly because you know, like at this carbon, there should be 4 bonds. There's not a formal charge, and so it's got to have hydrogen attached. If it's a radical, you have to show the dot for the radical because a lot of times the dot for the radical isn't charged. Right. Where am I at in my lecture? So much to do still. All right, so we're gonna practice bond line drawings. Okay, how many carbons are there in that first one? 5. 6? 5? 1, 2, 3, 4, 5. Yeah, good. So I'm gonna do bond line. Ready? Put a dot, and the angle is like a trigonal planar angle. It's a 120 angle. So you're gonna go 1, 2, 3, 4, 5. That is it. Yeah, and then you can just stop and count 1, 2, 3, 4, 5. And you're like, okay, I got it right. Because typically, what happens when people screw up, they'll go like this: 1, 2, 3, 4, 5. And then when they go back and count, they go, I don't know how I got 6. Like, oh, you know exactly how you got 6. That's how I got 6.
4 bonds, 5 carbons.
Yes. But just count 1, 2, 3, 4, 5. I don't analyze that much. I'm just like, okay. Next. 2, right? So 2 looks like that, which is weird. And then it's got to go to a nitrogen, right? And then 2, like that. And then I didn't do the BR yet. Where's the BR attached? On the nitrogen. Kind of looks like a bat. That's what you're going to eventually start doing. You'll start seeing things. You'll see like, oh, that looks like a clown.
It's like the Nike sign carrying
Yeah.
a bromine.
That's a bat carrying a bromine. The delusions are strong. Okay, so here's something that's a little trickier, right? This is CH3, CH2, but it's repeated. So one of these is a chain with these, and one of them is coming off this carbon. All right, so we're going to go like this. So when you see something like this, one is part of the chain. I forgot the is. And then the other is a branch. That's what we call it. Like a tree. Or a river. So I'm going to go again. That one is like this. 1, 2, 3, 4, 5. So it's actually this. Just like I drew in the first one. Which carbon, right, does the branch come off of? The middle one, number 3, right? Because this only has 1, 2, three things attached to it if it doesn't. And so one of the branches has to come off that third carbon. And you can just see it in the numbering where it comes off of the number. So we're going to go like this. And it's 2 carbons long, so it looks like that. Or you may have drawn it like this. It doesn't really matter which way that tail goes or the branch goes. And that's a dragon flying off with the body of a stick man.
That's what I said.
It's art, but it's science.
It's stick art.
Nice of you.
Are we gonna make models out of toothpicks?
So now this is a little trickier. This unit repeats, right? So CH3 and then a carbon and a nitrogen, and the Cl's are coming up the carbons. So how many carbons long is that? 3. So we're gonna go like this, right? And then we're gonna connect it to a nitrogen. And then because it's a nitrogen, we draw the hydrogens on it. Now on this first carbon, I have the 3 hydrogens. On these others, I have the chlorines, like this. I'm always trying to draw it so it looks like peace signs or upside down peace signs. That's the trigonal planar kind of drawing. It's actually tetrahedral, but we draw it like on paper. We draw it as like trigonal planar.
How do you know? Is it because it's like on the second? How do you know where to put the CL?
How did this one? Because the Cl is coming off this carbon. So this is the first carbon. This is going to be the second and third carbon because it's repeated. It's a unit that's repeated over and over again. Okay, so I've just been showing you like my propensity to start with an upward stroke. You could also draw these with a downward stroke first. And it's the same. It's just the direction I started my pen. You might be an upstroke person or you might be a downstroke person. I don't know.
So there's 2 CHCl's, right? That's
I hope so. Yes.
Yeah, so that
Yes,
means
you're correct.
where the Cl's touch the main ziggle or whatever that
The parrot chain.
is where
The what did you call it?
Ziggle.
Ziggle? Never heard that one. I like that.
Invented that right now.
Yeah, this is the ziggle. So yeah, where the chlorines are touching the ziggle. That sounds dirty. Stop saying it. Where they touch the parent chain, that's that unit there.
It's a ziggly line.
And that's where the CH's are, though.
Yeah, because there's also a hydrogen here. I just didn't draw it right. Like if you wanted to fill it in, you would do that. But in a line drawing, you usually don't draw those. If it has to be shown as part of the reaction that the hydrogen is involved, and you'll learn when it's involved because we have chapters on like every kind of reaction. You'll learn when you have to draw them and when you don't have to draw them. So far, so good? Yeah, good.
You know, I'm randomly going to be thinking of that and still laughing through.
Yeah, that's when they start locking you up, so just be a little careful. Not speaking from personal experience. What time did this class start?
It's
An hour ago. 9:30. Okay, so we got like 45 more minutes. Perfect.
It's 10:28.
So we have to talk about polar bonds and polar molecules, and so it's nonpolar when. Okay. It's nonpolar when atoms of the same type are bonded together. That's the only time in organic chemistry, really. That's when it's nonpolar. Or it's CH. Because carbon and hydrogen's electronegativities don't vary that much. The difference between them is only about 0.4. And so this is, when you see this, especially when you see this, these are nonpolar. A molecule is going to be polar, right, if they have different electronegativity. And basically, carbon bonded to nitrogen or oxygen or fluorine or phosphorus or sulfur is going to be polar
That's Chenopsis.
without the H.
Chenopsis.
Yeah,
From
it's
Russia.
Chenopsis. And this represents all the halogens. There's going to be some polarity. You don't need to have the electronegativities for organic chemistry. It's never going to be that close. Okay? You're just going to be like, oh, carbon's bonded to another carbon that's nonpolar. The hydrogen is nonpolar. It's oxygen, well, it's polar. It's nitrogen, oh, that's polar. Oh, it's sulfur, it's going to be polar. Chlorine's going to be polar.
My brain is saying Chenopsis.
And in general, right, the electronegativity dictates the direction of the dipole. So with the separation of the charge, right, where the charge is going. And chlorine will be the negative, oxygen would be the negative, and nitrogen would be the negative with bonded to hydrogen. And when we draw the dipole, we draw a little arrow like this, right? That arrow indicates the direction the charge has moved. So I'm going to scroll a little bit. Just for completeness, right? Non-polar covalent bonds are less than 0.5 or 0.4 or lower is the way you should say it. And that happens to be, this is non-polar covalent. Polar covalent is basically everything else except for when a metal is involved. And when a metal is involved, it's ionic. Okay? So basically the rules you learned for nomenclature in 1A, non-metals together be polar or polar covalent, and if you have a metal, non-metal, it's ionic. Okay? And in organic chemistry, carbon and carbon and carbon to hydrogen are non-polar and everything else is polar. See, very nicely gives you the ranges, but you never use them, so there you go. Yeah, bigger the electronegativity difference, the more polar the bond. Yeah. And you can tell electronegativity trends. I think I got rid of the chart. Let me see something really quick. Yeah, I got rid of the chart. You know, the electronegativity trend is, okay, so I have my, this is my periodic table all these times. Where's the electronegativity highest? Because fluorine happens to be in the top right-hand corner. It's Friday, so I just want to use it. That's the highest electronegativity, right? So the closer you are to this corner, the higher electronegativity. Carbon's way over here. So always when you're looking at like carbon, hydrogen, carbon, this is non-polar, but then all of these are polar except for HI. But I will tell you the truth, that's kind of a lie. HI is actually polar. And then most of these are polar. When you get down to here, oh yeah, well that's dipole. This is polar. Yeah, these are all polar. Yeah, anyways. Those are an electronegativity difference. Those are dipole moments. I forgot that. But those are all polar bonds, or example of polar bonds. Only time it's not polar is carbon to hydrogen. Okay, we got to get a little bit into another kind of representation. It's called the electrostatic potential map. An electrostatic potential map is kind of a unique thing in organic chemistry, but it's not a difficult concept. So let's say you are hydrogen and you are chlorine. So you are an acid together. Okay. Which side is positive? That's positive, and you're negative, right? Dipole's pointing this way. So if I were to take a little charge meter to measure negative charge, and were to go around it like this and measure the charge, where would I be measuring negative charge high? It'd be on this end, right? Then it'd be over here, it'd be low, right? And actually the way the electrostatic potential map is generated is they simulate an electron charge around the structure after the model has been created. This is a molecular model that uses quantum mechanics. And they see where is the electron repulsion the greatest. And it's greatest over here and lowest over here. And red is used to indicate, because it's the greatest over here, there's a lot of electron density. So red, right, has the most negative electrostatic potential, a lot of electron density, and the most attractive positive charge. And then if you go on this end, this is blue, right? That's the least electron-rich or most positive part of the molecule, and it's attracted to negative charge. So blue is positive, right? Red is negative. And green is neutral. And where do we get our color scale from? It's Roy G. Biv, right here. Red is the most negative. Roy is the most negative. Blue, well, it's Roy G. Biv.
Roy GB.
Yeah, there's a if
Roy Game Boy,
there.
it works.
But yeah, that's the most positive. So that's a pretty standard drawing style. You'll look at lithium hydride has a very large negative hydrogen, a very large negative charge on the hydrogen. H2, right, is neutral, and HF has a very positive charge on the hydrogen, very negative charge on the fluorine. Okay, whew. Just trying to get through all this. Oh, orbitals. I didn't know how deep to get into this, but you do need to know this stuff. So I'm going to kind of go through this, and then we'll see where we end up today. Won't quite finish the whole chapter, that's okay. Orbitals are probability density maps of where electrons can be found. And when you have a node, that means there's no electrons. And so when I have a drawing like this, what orbital is this? It's a p orbital, right? It's a dumbbell shape. It says right here it's the 2px. Or you have an orbital like this, it's the 2py or the 2pz. These represent regions where you can find the electron. So like if you're here, there's a certain probability of finding the electron. If you're here, this is the node, there's zero probability of finding an electron in the node. This is wave behavior of the electron. When this is for the p orbital, the s orbital looks like that. This would be 1s. I don't know if you can read it. Barely. It says this is the 1s orbital. It's the only orbital types, subshell type that doesn't have a node. Is the 1s. But it turns out the 2s, we draw it big like this, but the 2s embeds within it the 1s. And the 2s actually has a node for the 1s. Not for the 1s, near the 1s. So literally the 1s orbital is the only one that doesn't have a node, and all the others have nodes. This is known as a radial node because it's around the center. It's around the radius. These are called what's the name? It's a plane, nodal planes. That terminology is not that important. I'm just telling you just in general stuff. And when we're talking about bond formation, we talk about overlap of orbitals. And in the overlap of orbitals, it's in that overlap region where we can place the electrons to create the bond. So typically where we get introduced to this kind of stuff in general chemistry is when we talk about this formation of the sigma bond. I'll talk about that in a second, between two hydrogen atoms. There we go. So, and I always tell the story when I do this, I always talk about my wife and myself. My wife and I met in graduate school, and I was in Greeley, California. Actually, I was at Santa Cruz. I was a little more exotic. Long hair, carabiner with a cup, and a backpack. That was me back in the day. And that would have been, one of these would have been me here, right? And then my wife was in Iowa, right? And then we didn't know each other. And so then we ended up going to graduate school together. And so we ended up graduate school together. And when we got to graduate school, I saw her electrons, and I thought, right? I think I'm attracted. I mean, like, you know, you're not the way you're thinking of it. But what happens is as the two orbitals get close together, right, there becomes a region of stability in the overlap where you can place electrons. And the closer the two get, right, the more the overlap, the more stable it gets down to this point here. Out here, this is when I was in Reedley or in Santa Cruz and she was in Iowa. And this is when we got to graduate school, and gradually as we grew closer together, right, our commonality, our overlap increased, and eventually we reached this sort of happy bond length, right? You know, like in any relationship, sometimes you get too close, and you're like, I need some space, and then so you back out and you're over here, but then if the relationship's gonna last, you go, no, that wasn't so bad, and you come back. And basically, your relationship is always going like this, right? And you find in the relationship that lasts a long time, you find a stable region. This stable region in an atom is called the bond length. In order to break the bond, which hopefully doesn't happen, but in order to, well, I mean like in your relationship, but if you're going to break a bond, then what you have to do is you have to overcome this amount of energy from here to here in order to get the bond separate. Okay? But what's really important about this whole discussion is the overlap indicates the quality of the bond. The quality or strength of the bond. One of the techniques we'll use in week 5 of the class actually is IR spectroscopy. You actually measure the vibrations of these bonds. That's what you're recording when you do the infrared spectroscopy, is the stretching of those bonds. Okay. Now, okay, so back for a second. This description usually comes when we're talking about valence bond theory. And we'll find out when we talk about hybridization, probably in the next lecture, is that atoms will hybridize just so they make more bonds. And the reason they do that is because when you make more bonds, right, you can release this much energy for every bond. And as you make more bonds, you become more stable by making more bonds. So if you can make more, then you do make more. That's what's going to eventually come out of this. Okay, one of the things. But when we talk about molecular orbital theory, pictures start looking like this. I'm going to draw pictures next to them in the minute I have. But this is like s orbital. This is a 1s, and this is a 1s. And in molecular orbital theory, we use quantum mechanics, so we use the wave functions for the electrons. And the wave functions can be either positive or negative. So this is also for the wave functions, but this one's positive, positive. This one's positive and negative. In chemistry, rather than drawing positive, 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 negative, in the drawings that you'll see in just a second, we use colors to designate whether it's a positive or a negative wave function. When you bring these two together and they're out of phase, what you end up getting is destructive interference, right? Destructive interactions, which creates what's called the anti-bonding orbital. So basically what we've been talking about when we talk about valence bond theory, we've ignored this interaction. We've just talked about this one. Like two atoms will come together, their wave functions will overlap to create a new molecular orbital. Right? And when you create this new molecular orbital, you put the electrons in there, and that's what creates the bond. But in reality, beyond valence bond theory, we have molecular orbital theories that says at the same time you can create this combination, you're creating this combination. This is the anti-bond orbital. And then I'll finish with this. So this is what the bonding molecular orbital looks like. When you take this circle and you bring them together, it'll look like this. When you take this one and the negative of this one, which they really should have done in a different color up here, they cancel out in the middle. And this creates a node, and the electrons are not stable in the node, so it's higher in energy. Because the electrons, right, want to be between the nuclei, because that's where the positive charge is, but the node keeps them from being there, so this one is unstable. Okay. I think I'll stop there. There's still quite a bit of this chapter. If you're going to be working on homework, you should get through the structure drawing stuff. Do a little bit of this. There's a lot of problems. Get as much of it done as you can.